All right, moving on, still reviewing. So let's see how much you remember about quadratic functions. Now, you need a way to be able to graph in here, and I know some of you have graphing calculators, but this is a very good website that you'll see me show some graphs, and I'll once we get to a part where you have to graph, I will actually show you how to use this website, so that'll be in a next upcoming video. And I should mention that they also have it for an app on your phones, which is cool. All right, this is where we left our last lecture, and we said, how could we find these break-even points? When we said, well, we just set revenue and cost equal to each other. That's fine. I distribute out my x, and I notice right away I have a quadratic function, because remember, you know when you have a quadratic, because the highest exponent's a 2, so that square term makes this a quadratic. So let's kind of go back before we do anything with that, and let's review quadratic functions. Second degree functions, sometimes they're called a square function. They're in this format, ax squared plus bx plus c, where a, b, and c are just real numbers, but a cannot equal 0, because if a equals 0, then 0 times x squared goes away, and you have a linear. The graph is a parabola. If this first term is positive, it opens upward. If it's negative, it opens downward. I had a teacher one time that said something about if it's positive, you're happy and your cereal bowl didn't dump out. If it's negative, your cereal bowl dumped out. I didn't get it either, but I thought I'd share it with you. So just the graph of x squared then would be the value of a in ax plus bx plus c is 1. There's a 1 in front of there, 1x squared. So it's positive, so this would be concave up. I can look at things like the domain, range, and the vertex, where the domain is what values can you plug in for x, and I think you can plug in any. The range, notice, are my y values, so it starts at 0 and then heads up to infinity. And my vertex is this point here. In fact, it's the minimum, and as you can see, that's 0, 0. Well, what if we stick a negative there? Then we can see this is concave down. My domain, I still can plug in any x's. My range, I'm looking here, and it looks like it's approximately -4 to minus infinity. But how would we get that vertex there? If you remember in algebra, and it may have been a while, and this is in your packet, this is the vertex, how you find the vertex with this formula. So remember, we have this ax squared plus bx plus c. So all we need is a and b, and we plug in here, and it gives me the x coordinate of my vertex. So I plug in negative b, my b is 4. I plug in 2 times my a, -3, and I get about 0.667 or 2/3, and I can see that that is my vertex. Now remember, that just gives me my x value, so to get my y value that you see there, I have to plug 2/3 back into my original equation, and that gives me my y. Because remember, f of x, we call f of x as our y. And so it gives me this point on my graph. We've mentioned before that the x-intercept is, of course, where the function crosses the x-axis or touches the x-axis, and it's also where y equals 0. Well, with quadratic functions, a lot of times you will hear these called roots, and how you find them is by setting the function equal to 0, and then you solve for x. Well, this is pretty easy to do when you have something linear, right? Is you simply set my function equal to 0, I move the 3 to the other side and divide by 2, so I can solve this pretty easily. However, it's not quite as easy with quadratic functions. There's certainly other ways if you can factor. You may remember something called completing the square, but what always works is the quadratic formula. So this is the ax squared plus bx plus c equals 0. I plug in minus b plus or minus the square root of b squared minus 4ac all over 2a. So let's see an example of using this. Find the x-intercepts for this quadratic function. Well, what I do is I graph it right away so I have an idea of my answer. So if I get 7 and negative 14, or if I only get one answer, then I know something isn't right. I plug everything into the quadratic formula. So my b is 4 minus b plus or minus the square root of my b squared minus 4 my a c all over 2a. And then just away I go. I multiply all this stuff out. I get 76. And so I just can put this straight in my calculator and I can get my lower value and my upper value. And as you can see, these look pretty reasonable about what my graph showed. So I think I did it correctly. And once again, remember this is an actual point. And it's when my y equals 0, so I can actually put a point there by putting my x, comma, my y value. All right, so we go back to our original problem, which was how can we solve this? And you might wonder, well, what we were just solving with quadratic functions is where it crosses the x-axis. Well, you can think of this cost line as the x-axis. So what I can do is take, and after I distribute this, I set it equal to 0, and then I just collect like terms, and I have this in the form of ax squared plus bx plus c. So now away I can go. I can plug this into my quadratic formula. Don't forget to separate your plus and minus, and I get my two values. So I also want to find the y values because remember all that gave me were my x values, but I want to plot points. So I take the 12.5, I plug it in. I should get the same y values, right? Because this is where they cross, where they're equal to each other. And then I use the other x value to get this one as well. Because remember, break even is when revenue equals cost, so these should be equal. I just zoomed in a little bit. This is the same graph. And now I see that I can add these to the graph, and definitely that gives me my break-even point. Well, what about some other uses for quadratic functions? I kind of hinted on this when we were looking at the vertex. This gives us a way to find maximum and minimum values. So that's kind of nice as well when we have this quadratic. Let's look at an application of revenue. The marketing research department for a company that manufactures and sells notebook computers established these following price, demand, and revenue functions. So my price, my demand is X. My revenue function with my demand still X. Price is the wholesale price in dollars. X is my thousands of computers that can be sold. R of X is my revenue in thousands of dollars. And they both have this domain that I can only make between this one, and notice these are in thousands, 1,000 and 25,000 computers. Find the value of X that will produce the maximum revenue. And then what is the maximum revenue? Well, away I go, I'm going to graph it. I'm going to graph and I'm going to see that it looks somewhere up here. Okay, I didn't show the x-axis, but I can see what my maximum revenue is going to be. And if I go back here, you might wonder, well, what did I graph? I graphed my revenue function because that's what I'm looking for, maximum revenue. So how to find the maximum value? Remember the vertex formula. But you need to go ahead and distribute this x out because you need it in this form, ax squared plus bx plus c, but our c just happens to be 0. Remember what you're maximizing. You're maximizing revenue. So if I plug everything in, I get my x value. I take and I plug my x value into my formula, and yes, that looks correct with what my graph looked like. I can plot the point to verify it. And so I would say about 16,667 computers, because remember that this was in thousands, so I converted 16.67 into thousands, will produce the maximum revenue of this 16,667,000. Well, what is the wholesale price per computer? Well, we have a function right here that's about price that produces the maximum revenue. Well, we just found our number of notebook computers, so I simply plug that in, and I can see that I get my price, my wholesale price that would produce the maximum revenue would be $1,000.